Welcome back. In the last lecture, we discussed first-order reaction kinetics, or kinetics that are observed when you only have one reactant in a chemical reaction. Now let's explore second-order reaction kinetics and zero-order reaction kinetics. What's that? By the end of this video, I want you to be able to determine whether or not a second-order reaction can be suitably treated as a pseudo-first-order reaction, and we'll explore a little bit what that means. Calculate second-order reaction rates when reactant concentrations are equal, and finally describe the conditions when a zero-order reaction may be noted. So we'll discuss a little bit more, of course, what a zero-order reaction is. So here again, for a reaction A plus B yields C, is the mass action expression for that equation. The change of A with respect to time is equal to the rate constant, K, multiplied by -1, multiplied by the concentration of A multiplied by the concentration in B. And I set up this little example problem where A plus B yields C, and the initial concentrations of A and B are different. And you can see that the reaction rate declines pretty precipitously, and this is because as A and B are consumed, B pretty rapidly goes to 0. B is the limiting reagent, and so this whole reaction term, shown up here, rapidly goes to 0 as well. But what exactly are the equations that describe the time evolution of these concentrations A and B? So starting at time 0, can I say what time 1, or time 500 as I have here, time 1000, what those concentrations will be? This again, like in the last lecture, will require integrating this expression, but it becomes a lot trickier because now you have two variables, A and B, that you need to integrate over, and not just one as we did in the previous one, A. So we're going to consider a few different cases of the relative relations of A and B and how that affects the integral that can describe the time evolution shown in this graph over here. And the first case that I want to consider is what happens if one concentration of reactant, say B, is much greater than the concentration of A. So in this example that we have over here, these concentrations are different, but they're not that different. A starts off at 1, B starts off at 0.7. What if A started off at 10,000 and B started off at 0.7? What does that do to this expression up here, and can that lead to a useful simplification for us? Let's find out. Let's consider the case, just to begin with, where the concentration of B is much greater than the concentration of A. So let's say, for instance, at time 0, our starting concentration of A might be 0.0001 molar, and the concentration of B starting off might be 1 molar. So A is much smaller than B. So at any time in the future, when you've used up all of the A, even if you use up all the A, so A at time t equals 0, your concentration of B at time t, because there's so much more of B than A, will have hardly changed at all. Even if this reaction proceeds to use up all of A, you'll have B in such excess that at time t you'll have 0.9999 molar concentration of B. So B hardly changes as the reaction proceeds entirely to completion based on the limiting reagent A. And so because B changes very little, this B up here in this term also changes very little as the reaction progresses. And so what you can do is essentially treat this B as a constant, plugging in B0 into that B. And then this simply becomes a first-order rate equation, because this is a constant, this is a constant. It's only dependent on one variable here, A. And so we can rewrite this second-order mass action expression as simply a first-order mass action expression, dA dt equals -K times B naught times the concentration of A. And again, this is now just a constant. And so if we want to know the concentration of A at time t, we can just use the integrated first order rate law that we used before. A at time t equals A naught, or A times 0, times E raised to the negative k, and then we use this whole thing as the constant, negative k, times the concentration of B at 0, times T. And so this is a nice way to simplify problems when you have one reagent that's far in excess of the other reagent. You can just restate this as a first order reaction. And this is an approximation, but it's a pretty darn good approximation. And what we call this is the pseudo first order rate law. And a good rule of thumb is that, say, if you're calculating A to 2 significant digits, that answer will be right if these differ by at least the number of significant digits plus 1 in their orders of magnitude. So this is a difference of 4 orders of magnitude between the two concentrations. And if we want to calculate A to 2 or 3 significant figures, then that would be a fine approximation to make. So this is a great tool to have in your toolkit because it dramatically simplifies the number of variables that you have to include in your rate law, and therefore makes the calculation a lot easier. So what we've discovered here is a very useful simplification that you'll use a lot in this class, and that's the simplification of the pseudo-first order reaction. And just to summarize again, a pseudo-first order reaction is a second order reaction where the concentration of one reactant so vastly exceeds the concentration of the second reactant that the reaction will behave approximately like a first order reaction. It won't behave exactly like a first order reaction, but the approximation is good out to, n number of decimal places. And again, the formula for this, where A is the limiting reagent, so A is the one that there's a very tiny amount of, and B is the excess reagent, will be the concentration of A at time t equals the concentration of A at time 0 times E multiplied by negative k, the reaction constant, multiplied by the concentration of B at time 0. So this term, negative k times B0, or B naught, is a constant, times T. And if you just combine negative k times B0 into one new reaction constant, you call it like K star or something like that, you end up with exactly the form of the first order reaction equation. Okay, so let's again consider the mass accident expression for a second order rate, which is negative k times A, concentration of A, times the concentration of B. And now let's assume, and this is reaction A plus B yields C. Now let's assume that A and B are equal in their starting concentrations. So A naught equals B naught. Or, alternately, let's assume that A and B are actually the same chemical, such as in a reaction like 2A yields C. Then, this rate expression doesn't have to be written as the function of two variables, but it can instead just be written as a function of one variable. So we'd write dA dt equals negative k times the concentration of A squared, if A equals B, or if they're just 2A in the reaction. And so this, again, is a rate equation that we can easily solve to determine what the concentration of A will be at some finite future time, given a concentration at a present time. And we just proceed by integration, again by separation of variables, so we can just divide through by A squared, so we end up with concentration of A raised to the negative 2, since I divided through, equals negative k dt. I'm sorry, this is concentration of A, negative 2 dA. Okay, now that we have the variable separated, again, we can just integrate both sides with respect to the differential that exists on each side. And this side, by application of the power rule, comes out to be negative 1 over the concentration of A. And this side over here ends up being negative kT. Divide through by negative 1 on each side, and you end up with, we can just erase these negatives. 1 over A equals kT. Okay, so now let's evaluate this from time 0 to time t. and from concentration A0 to concentration A at time t. And this, again, is the variable that we're solving for. And we can write this as 1 over A at time t minus 1 over A at time 0 equals kt minus 0 plugged into t is 0, so minus 0. Okay, so this is pretty nice. Now I'll just bring this up here and we can rearrange this a little bit. Let's add 1 over A0 onto each side, and we end up with 1 over the concentration of A at time t equals kt plus 1 over A0 and so this is a nice little expression here, and this is nice because this is a constant and this is a line with a slope, so this has a linear relation to this concentration. And if you want to just solve for this, then you can just multiply through by -1, and you end up with your concentration of A at time t equals 1 over kt plus 1 over A naught. Okay, so this is the integral form of a second order rate equation when your starting concentrations of A and B are equal, or they're just the same thing if it's A times A. So stick this formula in your pocket for use when you're solving these equations. Okay, so the last case I want to consider is when A does not equal B, but this assumption that B is way larger than A that let us do the pseudo first order reaction also does not hold. What can we do then? Well, we can integrate this expression again, as usual, but this integral really sucks. Who wants to deal with something like that? So, in this class, you won't be responsible for solving problems where A does not equal B, but those values are pretty close together to each other. You won't be responsible for solving that in an analytical sense, at least, using equations that give you an exact answer. But there are ways to solve this equation using approximate methods or numerical methods, which we're going to cover in another class. So stay tuned for that. Okay, now I'd like to discuss zero-order reactions. And again, a zero-order reaction is a reaction where there are no activities of reactants that occur in the rate law, such as over here. The change in A with respect to time is simply equal to -k. You'll notice that there's no concentration of A or anything else in this rate law. And this integrates very simply into simply the concentration of A at time t is equal to the concentration of A at time 0 multiplied by -kt, with t being the time that's elapsed since time 0. Now, the law of mass action, though, says that concentration should always play a role in determining the reaction rate. So how can we have this seeming violation of the law of mass action? Well, first let's approach this by analogy, and I think a good analogy is a vaccine line, hopefully something that everyone's going to become familiar with very soon. And let's consider what the rate-limiting step of vaccination is here. Is the rate-limiting step the number of people that are standing in line? No, you have a bottleneck up here at the front desk. The rate-limiting step is the actual vaccination process. So the number of people standing in line doesn't determine how fast these two vaccinators work. It's only their intrinsic ability to work and vaccinate people that determines how fast people are getting vaccinated. So that's the analogy. Now let's consider this in a chemical sense. The big example of this occurs is where you have a catalyst, and this catalyst is in smaller quantities than the number of reactants, vastly smaller quantities than the number of reactants. Now you'll recall that a catalyst is something that speeds up a chemical reaction, but doesn't get produced or consumed in that chemical reaction. And so, if this reaction of blue boxes turning to purple boxes happens very, very slowly without a catalyst, but it happens very quickly with a catalyst, and there's not a lot of catalysts in this system, then the number of blue boxes lining up to get catalyzed to turn purple will not determine the rate at which this catalyst can produce purple boxes, because the rate limiting step, the bottleneck in this reaction, is simply the number of catalyst sites available to catalyze the reaction. As long as the number of blue boxes here is in vast excess of the number of catalysts to make this conversion, then you'll have something that approximately obeys a zero-order rate law. In these last two lectures, we've explored elementary reactions, or reactions that have one reactant or two reactants at most. But in this next lecture, we're going to explore what happens when you have multi-step reactions. So big, long reactions with multiple reactants and multiple products. They're actually just the sum of a bunch of elementary reactions coming together to form one big overall reaction. How can we gain some analytical tractability on these reactions to understand them in the terms of elementary reactions? And when can we make some useful simplifications that allow us to understand an entire chemical system without understanding the nitty-gritty of each elementary reaction that goes into that overall reaction that we're interested in? We'll explore both those topics in the next lecture, so stick with me.